Hey guys, Luke here, and welcome to the channel ENGR459. We're all just a bunch of students trying to better our knowledge and understanding of electromagnetism. So hopefully, through these video lectures, you'll either learn or get a nice refresher on key electromagnetic concepts. Enjoy the video! In today's video, we will dive into core concepts of electromagnetic theory, discussing polarization, reflection, and transmission of electromagnetic waves. My goal of this video, as well as the video series provided at this channel, is to tie in core concepts of electromagnetic theory and relate it to real-world applications as we are in engineering channel. Now, the first topic I will talk about is polarization of an electromagnetic wave. Now, before I get into that, I have to kind of review the fundamentals of what exactly is an electromagnetic wave. So if we look at, if we solve Maxwell's equations, we come up with the plane wave solution. And the plane wave solution is basically just this to negative j beta z x hat, with beta being your wave vector and x hat being your x component of the electric field. Now with this in mind, I'll plot this electric field with respect to time. So as we see here, as time goes on, we have an oscillation in free space, and this oscillation is the electric field, and it is going along the beta direction. Now, after we shortly discussed the plane wave solution to Maxwell's equations, we now move on to the polarization of an electromagnetic wave. Now, polarization is defined as the locus of the tip of the electric field in the plane perpendicular to the direction of propagation at a specific time t. Now, if we draw that out, I'll draw a graph here with this equation in mind. I'll draw a graph as this plane waveform is in complex domain and time harmonic form. We have an associated e to the j omega t component. So now, if we trace the electric field on this, we can see it oscillating in the x direction. Hence, this wave is linearly polarized in the x direction. The type of wave we just described is a linearly polarized wave. However, there are other types of polarization states, such as elliptical and spherical. To illustrate this, let's go back to the plane wave form and modify it a bit. Adding a y component still keeps it linearly polarized, however with a diagonal locus. But now let's examine the case when I add a phase shift on the y direction. So now if I add a phase shift, here e to the j side, the locus is now, if I trace it out, a circle with radius e naught. Hence the term circular polarization. So after discussing polarization, we will now move to reflection. So in discussing reflection and transmission, I'm going to really try and pose a problem and try to solve it. So what happens when an electromagnetic wave propagating in one simple media encounters an interface, and that interface is the boundary of another simple media? And here I'll draw this problem. But first, we need to define a couple key terms. First of all, we need to define the plane of incidence. Now, the plane of incidence here is the plane that contains the wave vector of the electromagnetic wave, as well as the normal vector of the interface. So here we have an electromagnetic wave propagating in one medium of epsilon 1, mu 1, therefore in n1. And here's epsilon 2 and mu 2. In the remaining of this problem, I will assume mu 1 and mu 2 equals 1, just for simplicity. So I have an electromagnetic wave propagating and hitting the interface, and while this happens, it causes a reflected beam to appear as well as a refracted beam. Here I note beta I as the incidence wave on this plane of incidence, beta R being the reflected wave, and beta T as being the transmitted wave. I also define a normal to the surface of this interface, which is right here. Another key term we discuss here is the polarization states of the electromagnetic field on the plane of incidence. Now this will be slightly confusing as we recently just discussed polarization, but this is completely different. So the two polarization states in this section are TE and TM, transverse electric and transverse magnetic. Transverse electric polarization state is basically defined as the electric field pointing outside of the plane of incidence. This is also the same with transverse magnetic fields. So now let's apply the transverse magnetic polarization to this problem and try to solve it using Maxwell's equations to understand the reflection and transmission effects. So here we have the electric field inside the plane of incidence, EI, with the magnetic field outside pointing out of the page. We can now describe the relation between the incident, reflected, and transmitted waves using the time harmonic solution to Maxwell's equation as well as the boundary conditions of Maxwell's equations. As we know, at the boundary, the fields must be continuous to satisfy Maxwell's equations. A couple of conditions can be derived from this plain fact. First of all, the angular frequency dependency, omega 1 equals omega 2 equals omega 3. The frequency of the transmitted of the light transmitted through does not change. Secondly, we can derive the law of reflection. If we have beta Ix equals beta Rx, we can deduce that beta I sine theta I equals beta R sine theta R. Now, as we know, beta I equals beta R, we can then conclude that theta I must equal theta R. This is the law of reflection. Secondly, is Snell's law. In the first case, we had the reflected and incident beams being in the same medium. Now, the same laws apply when going through two different mediums. So we write beta I sine theta I equals beta T sine theta T. Now, beta I can be written as beta naught, which is the wave vector in free space, times the refractive index of the medium. Beta T can also be derived the same way, equals beta naught nt. Therefore, we have Snell's law, which states n1 sine theta I equals n2 sine theta t. In the same manner we derived the relationship between the incident, reflected, and transmitted angles, we can now use the same arguments to derive the relationship between the incident, reflected, and transmitted electric field and magnetic field. As the electric field and magnetic field are continuous at the boundary, we can now derive the following equations. We have EI cos theta I plus EI ER cos theta R equals ET cos theta T. Now, knowing that the magnetic fields are continuous at the boundary and that the magnetic coefficients equal H1 equals E1 over eta 1, we can now derive EI over eta 1 minus ER over eta 1 equals ET over eta 2. Notice the negative sign here and the positive sign here. The negative sign is here because the magnetic fields are flipped in TM polarization state. From these equations, we can now derive the Fresnel coefficients for reflection and transmission. For the TM case, RTM is the ratio between reflected and incident beam, as well as TTM, transmitted TM, is the ratio between transmitted and incident beam. Now these equations simplify to the following using algebra and trig. Now let's examine a special case of transverse magnetic polarization. To further examine this concept, let's examine the reflection coefficient for TM polarization, where the reflection coefficient is 0. The angle that satisfies this condition is known as the Brewster angle. This angle is also known as the polarization angle, as only one form of polarization can exist, the TM polarization. By setting the reflection coefficient to 0, we have eta 2 cos theta t equals eta 1 cos theta I. Now here in this condition, theta I equals theta b, which is the Brewster angle. Now we solve this equation with a couple of trig substitutions. We have sine squared theta b equals 1 minus mu 2 epsilon 1 over mu 1 epsilon 2, all over 1 minus epsilon 1 over epsilon 2 squared. This allows us to find, in most cases, mu 1 equals mu 2, as most materials are non-magnetic. Therefore, we can simplify this equation, and this is known as the Brewster condition, where sine theta b equals the square root of epsilon 2 over epsilon 1 plus epsilon 2. Now, an interesting application can be derived from the Brewster angle. For example, a rainbow has an epsilon value of 1 and epsilon 2 of 2.25, which corresponds to the rain droplets. Now, the Brewster angle of a rainbow is 44 degrees, meaning that if you tilt your polarizing sunglasses 44 degrees, the rainbow will completely disappear, as one form of polarization will disappear as well. As we derived the reflection and transmission coefficients for TM polarizations, the same can be done for TE. Here are the reflection coefficients for TE polarizations. T. Now, as we did with TM polarizations, we will now look to see if the Brewster condition exists for TE. Setting the reflection coefficient to 0 of the T polarization gives us this following equation. Setting RTE equals 0 gives us the following equation. Eta 2 cos theta I equals eta 1 cos theta t. Therefore, we arrive to sine theta b squared equals 1 minus mu 1 epsilon 2 over mu 2 epsilon 1, all over 1 minus mu 1 over mu 2 squared. Now, as said before, most materials, we have mu 1 equals mu 2, which is relatively equal to 1. Therefore, if we have mu 1 equal to mu 2, sine theta b squared would go into infinity, and the Brewster condition does not exist in TE polarization. This is why we call it the polarization angle, as there is not possible in the real world to have this TE term for the Brewster angle. To summarize, throughout this video we discussed polarization of electromagnetic waves, as well as reflection, transmission, and the special case of the Brewster angle. Thank you so much for watching.